few minutes about interoperable streaming media tracing. This is a work from the CTA Wave project. It's the Consumer Technology Association and the Web Application Video Ecosystem. And I wrote them there because I never remember what the acronyms stand for. The Streaming Media Tracing Working Group is it's a group of folks that have started to define the problem, and we have an idea of where we think the solution is going to go. But it's pretty early days. So I can't tell you about what the Streaming Media Tracing Project is. What I can tell you is about a possible future where we have a streaming media tracing and what we think that is probably likely to look like. So let me start with a story. And I want to tell you a story that about Jay. And Jay exists in this hypothetical future wherein this work is done and well deployed. And Jay is a regional CDN operator. And they have a problem because one of their clients has come to them and said, things are slow. And Jay's like, well, what do you mean things? And what do you mean slow? And the client's like, I don't know. There's like rebuffering and stuff. Jay is like, okay, well, that's better. Do you have any logs? And the client said, yes. And Jay's configuration is not necessarily super straightforward. It's not that complicated, but Jay is not the only participant in this ecosystem. You have clients, and they talk to the CDN, but there's a CDN above Jay, and there's an origin above that. And so slowness could be coming from any of a variety of places, right? It could be in the clients, because clients are sometimes slow. It could be in Jay's CDN. Jay is keenly concerned about this. And it could be upstream. And that would make them fairly pleased because it would be somebody else's problem to fix. But ultimately, they need to figure out where the problem is. So they asked the client, send me the logs. And fortunately for Jay, all of the participants in this community participate in the streaming media tracing ecosystem. And so let's talk for a minute about what that ecosystem looks like. And the answer is, it looks a lot like what the streaming media workflow looks like. There are humans that use their senses to consume content from a client that presents it to them. And that client gets its data from a CDN that serves it to them. And the CDN gets its data from an origin that stores it. But the content doesn't spawn ex nihilo on the drive of the origin. Rather, it's pushed there by a packager, which gets it from a transcoder that gets it from, that's going to get it ultimately from something that creates it, a camera or a creative program of some sort. And so this is a relatively typical, although certainly not the only, streaming media workflow. And when we talk about tracing it, we want the trace to look like what the workflow looks like. And there are kind of three important regions that we identified. And the first one is the pull, right? The client pulls from the CDN pulls from the origin. And this section gets a lot of attention. The pull gets a lot of attention. We understand this as typically an HTTP approach, but it doesn't have to be. But it's request driven. And so we have a request and we have a response. And we want those traces to contain that information. And we also have the push, right? Where something creates it, it pushes it to a thing that processes it, usually a couple of different things. There's a pipeline, and then it eventually lands itself on an origin, whereafter it can be requested. But if this was all we had, we wouldn't actually have enough, because we need to get the data off these boxes somehow. We want to have a standard format to export them. And they can all be exported to the same place because we want them to be interoperable. But they can also be exported to different places because in a typical workflow, these participants might be operated by different entities. And we'd like them to be able to export and decide what they're going to do with their data. It's very important that all of these components are opt-in. So now let's talk about what this looks like when we actually model it. So we start, with a client that gets information from a CDN, that gets information from an origin, that gets information from a processor, that gets information from a creator. And all of these participants on this thing, these boxes, are services. So this is what we're going to call them. Because we often think of them as hosts, but we want to abstract that away a little bit. And so we call them services because they could be containers, they could be processes, they could be functions. There's a lot of different things that these participants, these services could be. And the arrows represent single transactions, some data that moved, some data that was gotten from a place. And in this model that we create, we want to be able to attach metadata. We want to attach information about these states and whatnot. And so each of these services can have metadata. The example here is timing metadata, because obviously timing is super important if we're going to talk about calculating and determining latencies. So timing metadata, but also data about what its name is, data about what protocols it's using, all of that sort of thing. But the services aren't the only things that can have metadata. You can also have metadata about transactions. And this is really important because not all transactions are successful. And you might have multiple transactions from a given service. We'll talk about it in a second. And one of the most useful information about transactions is information about why they failed. You might have a more complex structure. For example, your processor might have multiple creators. You could have 2 cameras multiplexing into one video. It might be useful to capture that information. It might not be. You could have a CDN that contacts one origin and then the other origin because maybe something's broken. Sometimes something's broken. So if we take this model, the one on the screen here, and we encode it into an HTTP header, a response header, the sort of header that you might see in that poll section of our process. It might look like this. We actually suspect it's going to look a lot like this. There's no extra metadata on here. I just put the names in there because if we start adding it in, it gets unreadable. But the important thing to understand here is that, first of all, we're using structured field values, so you can use standard processors. We have a list of sublists. And this is important because each of the list members represents one of those services from the previous page. So that last line there is the client box. It represents that. And each of the sublist members, the indexes, are transactions. And we use relative indexing in order to create the graph. So that 0 is 0 indexed to the element above. The client is connected to the CDN. The CDN, we can see, has two list members in it. That has a 4 and a 0. The 4 indicates that it first contacted index 4, and its second contacted index 0. So it started with a request to the broken origin, and then it made a request to the regular origin. Now, I helpfully named them here so that we can tell them apart, but it certainly starts to tell a story when we see this trace. The processor got its content from a pair of creators, and we have an entire graph. This is the graph that we would have displayed elsewhere, but it's stored conveniently in an HTTP header, and it's a header that, because it uses relative indexes, each participant in the process doesn't have to fully parse and understand the incoming headers. It can just add itself at the end. If it needs to, there are some cases, if it's got multiple parents, it might need to count commas. But counting commas is fast. But HTTP isn't the only place these can be. This is a very early design. This is not subject to any sort of consensus. This is among the more hypothetical of our hypothetical futures. But you can imagine this data exported to some sort of an aggregation unit. It's presented here in CBOR, although it may turn out to be in JSON or some other self-described format. It's useful for an exported format to indicate which entity did the exporting. In this case, it's an export from the client, we can see. And it looks the same. The model is represented the same in this format. List members are services. Sublist members are transactions. And you can create the graph from this format in precisely the way you can create the graph from the other format. So let's go back to J. J pulls the log from the client. And J looks at it and says, okay, well, there's a client. And the client connects to my CDN, to jcdn.example.net. That's great. And jcdn.example.net made one request up to e1.ucdn.example.net. That request also has an error on it, a connection error. This strongly suggests to J that there was something wrong with the connection to e1.ucdn.example.net. And in an ideal scenario, there will be extra information on here, like how long did I wait before I canceled? Was it a connection refused? More information, certainly. But then you wouldn't be able to read it on the screen. And then, after that, it made a second request up to e2.ucdn.example.net, which made a request of the origin, and clearly we got the data. And so what we see from this log is that the slowness is the result of a failed connection to the origin. If we only had a log that went through the successful portion of the transaction, well, it would look like JCDN just took however long it took to time out to the first upstream edge in order to contact the second edge. But there was nothing wrong with the second edge. And so a flat, non-tree trace would have misled us. Having the full tree doesn't mislead J. J knows I need to check the connection. Maybe e1.ucdn is broken. Maybe there's something wrong on the network link, but they know exactly where to look. And that's what we want. We want all of the participants to be able to determine, both in the moment and after the fact as a post-mortem, where trouble happened and where data moved, how long it took to move, how it was transformed along the way, and all of the things that tell us what we need to know in order to be good, efficient participants in the information transformation and transmission ecosystem. And with that, questions?
Any questions for Chris about media tracing? Yes, sir.
Thanks. Hey, so that could be valuable. I definitely see it from a troubleshooting standpoint where I'm doing curls and whatnot, and I can see the headers. But in my experience, it's hard to log the response headers from an application and client player standpoint. What do you think about that? Do you have a way to address that, or are you thinking of logging that in with some other mechanism, or?
So there's a couple ways to do it. Clearly, you can just log the response headers, right? That's one option. We do want to have an export format that is nice and terse that can be sent off so that any sort of a participant that wants to and is aware of the system can log them in that format and send them off. We also want to make it so that if a participant doesn't log, like Say your clients just don't keep any logs that you can get to. Well, you can still get 90% of the information from the edge. Maybe your upstream CDN doesn't participate, but your origin does. Well, you can still get 70% of the information. So the goal is to degrade gracefully. You're right, it's hard. We can't solve all the problems, but if we define formats that are efficient, maybe we can make it a little easier.
In a quick format, like a lot of the CDNs I work with, they don't log the response headers their response headers that they're sending to the client. So there's a gap there that I'm seeing. I know it can probably be solved somehow, but.
Right, so one of the things that's really useful is because this information moves with the data, whenever any participant that realizes the data has gone awry, they can take that opportunity to log just that data. So you can have a CDN, for example, that only logs the response headers for this particular request that failed to get to a client. Or if it identifies clients that are particularly troublesome, maybe it logs those. You can apply sampling to this. This is a mechanism for communicating data and doing so in an interoperable way. It doesn't actually mandate what data you have to store, and it gives you the best opportunity after the fact. When you know something has occurred, you don't have to log it before the error.
Thank you.
Hi. Not so much a question, kind of maybe more of a comment. Since you're in the early stages of developing this, I would encourage maybe look at open telemetry.
Oh, yes, absolutely.
I figured you were probably aware of what's going on there.
It was almost a slide in here, but if I put all the slides in here I want, happy hour would be at 11 p.m. And everyone would be, the room would be empty. But yes, one of the things you can do with this is, so open telemetry requires all of the participants to log like in the moment. And so if you only have the logs from some of the entities, you don't get the whole picture. Whereas with this, what you can do is you can take that export format and it maps one-to-one to open telemetry formats. It's actually not one-to-one, it's one-to-many. And that's part of the problem, because one of these traces actually turns into a couple of open telemetry entries. And so you can absolutely have your export where I put a database. You can absolutely have that thing just immediately reformat that into open telemetry and send it into your existing telemetry solution. The goal is for the information to be transformable.
Great. Yeah, it'd be good if you guys could collaborate so that we have one common way to do that.
Yes, yes. In fact, I've talked to them to some extent. They don't solve, the open telemetry solution doesn't solve all the problems we need solved, but it solves a lot of problems, and there's a lot of existing implementations that are very useful. And so,
Great,
yes, observed.
All right, thank you. Thanks, Chris.